Hello, everyone. This is Mr. Younger. I'm here to teach you a little bit about center of mass, specifically how to calculate center of mass and to explain to some extent exactly what it is. Let me get started by showing you my iPad screen. So where we're going in our physics class right now is we just finished learning about momentum. And one of the neat things is that conservation of momentum problems can be solved with also this concept called center of mass. So a lot of, if not all of, the center of mass, or excuse me, the conservation of momentum problems that we solved can almost always be solved with the center of mass solution as well. So that's one of the reasons we bring this in here. But the other reason is the big picture of physics is that we can actually treat an object, a full physical object, like this water bottle, for instance. It obviously has a physical dimension. It's not a point particle. So when I apply a force, not only does it matter which direction and what the magnitude of the force is, which makes, force a vector quantity, but it turns out that it also matters when you're dealing with a physical object that has some size. It matters not only magnitude and direction, but also the location, because if I push up here, that's one thing. But if I push up here, that tends to rotate it. If I push up this way, that tends to rotate it the other way. If I pushed up on this end and down on this end, that's going to rotate it even more. So ideally what we'd like to do is be able to treat physical objects that have some physical dimension. We'd like to treat them as a whole, and it turns out that such physical objects can be treated as the way their center of mass behaves, which is basically just like a point particle. And then we would choose like another point within the body, for instance, assuming that it's a rigid body, so that all the individual particles making up the body are always exactly the same distance away from every other particle, so that they never compress or stretch or anything like that. And then we could take one of those other points in the body other than the center of mass and imagine a line connecting the center of mass to that. And then we could watch that other point and see what it does. So we actually have a center of mass that moves like a point particle, but then we'd have this other point that might rotate around this way or this way or this way or that way or all sorts of stuff. That's ultimately where we're going. So in order for us to better understand that application of physics to full-size bodies, we need to have some understanding of center of mass. So that brings me to this specific definition of center of mass that I've made up and given to you. So it says the center of mass. There is one point associated with an object called the object center of mass, which is abbreviated cm. That follows the same path as a point particle when it is subjected to the same net force applied to the object. So, in other words, what we're saying is if you can watch how an object behaves when a certain set of net forces or a certain set of forces causing a net force is acting on it, there's one point within that, possibly within the geometry of the body, but possibly outside of the physical body itself, that's called its center of mass. And that particle, or excuse me, that particular point is going to behave just like a point particle that had exactly the same forces acting on it. That point is called the center of mass. So now we're going to use sort of that idea of what a center of mass is to make some sense of a formula or to come up with a formula for it. So to get a feel, what I've drawn here is a green sort of plank that we can treat like a seesaw balance, and it's sitting on a fulcrum, which is a little black triangular prism that you see there. And what we know is if we imagine putting a mass m1, some distance x1 to the right of the fulcrum, as we have in the drawing here, you might ask yourself, well, where would I have to put another mass uh, on the left side to regain the balance? In other words, if the actual balance was frictionless and perfectly balanced and all that good stuff, then that beam is more or less irrelevant other than it holds the pieces together, but it would sit perfectly still as long as it's balanced. So as soon as we put a mass m1, a distance x1 away, it's going to tend to rotate in a clockwise direction as seen by this diagram. In other words, the right-hand side will tend to go down and to the left. The left-hand side, the left-hand end will tend to go up and to the right. So it'll go up and to the right, just like the right-hand side goes down and to the left. That's causing the rotation. So we know if we put another exactly the same mass, m1, to the left-hand side of it, exactly the same distance away, x1, that would stop it. Now, we could, in principle, find other masses M2, for instance, that we could stick a different distance x2 away, and by trial and error or by learning about torque, we could figure out exactly what that M2 and x2 would be, so that it would still balance. But right now, all we really consider or caring about is this one instance where I take one mass M1, put it a distance x1 to the right of the fulcrum, and then what we discovered is we can put another mass M1 exactly to the left of it, the same distance away, and that will balance it. So if we think about that, then we see in some sense that other point where we put the mass M1, that sort of is acting like the center, like a equivalent of the center of mass, because it has the same forces subjected to it, specifically the force of gravity, which is downward and is M1 times G, acting downward on the right and acting downward on the left. Now, the other thing is, it turns out that ability to rotate is not only dependent on the mass, in fact, it's directly proportional to the mass, because if you doubled the mass, the idea of it rotating would be twice as severe. Again, we don't necessarily know what I mean when I'm saying that yet, but I'm just telling you that it should seem somewhat reasonable that if I put, 50 pounds on the right hand side, that would make a big deal at 5 centimeters away. But if I put 100 pounds at 5 centimeters away, that would make twice as big a deal. So we can see that this ability to rotate does depend on the mass. But here's the other thing. What if we didn't consider changing the mass? What if we considered using the same mass, but instead of it being 5 centimeters away, it'd be 10 centimeters away? Well, if you have any experience with working with wrenches or trying to open bottles, or anything that requires a rotation, what you notice is that not only does the force that you're applying matter, but where you're applying it matters too. So if you're actually trying to, for instance, open a door to a room, if you grab the door right next to the hinge, you're probably not going to get it open. Whereas if you go to the other side of the door as far away from the hinge as possible, it's pretty easy to open. So in that sense, it turns out that the ability to rotate is also directly proportional to the distance away from the fulcrum, or the axis of rotation. So we now have that the ability to rotate depends not only on the mass or weight M1G, but it also depends on X1. So in fact, it seems reasonable that M1 times G times X1 has some magical feeling that tends to rotate. In fact, that's ultimately going to be determined to be what we call torque, Torque. So if we do put that mass M1 to the right of the fulcrum, a distance x1, then we could put another mass M1 a distance to the left of the fulcrum, a distance x1, and that would balance it. But now, what if we tried to put a mass M1 at a distance x1, and then we tried to put a mass M2 at a distance x2? If we did that, we could, in principle, put a mass M1 to the left at a distance x1, and then put a mass M2 at a distance x2 to the left. But that wouldn't help us here. That would balance it, but it wouldn't help us. What we want to do is, based on our definition of the center mass, we would like to find one spot to the left of the fulcrum where we could put the total mass, big M, which in this case would be M1 plus M2, since I'm now using two masses. We'd like to find one distance x to the left that we'd actually have to put the mass, big M, which is M1 plus M2, so that it would balance. Well, you don't necessarily know how to do that yet, but you could figure it out once we study torque. But for right now, what I want to just argue to you is that we're going to put a total mass on the left that's equal in magnitude to the sum of all the masses on the right, but we want to put it one distance away, and then it'll act just like a particle, because we're actually imagining this new mass, this M, capital M, which is M1 plus M2 in this case. We're imagining that like a point particle, and we're imagining it being applied a distance x to the left, and I'm specifically going to call that x to the left xcm, which is the distance to the center of mass, and it's as measured from the axis of rotation. So if I do that, then what I can see is, in principle, if I took two masses, M1 and M2, and put them at two distances, x1 and x2, then I would get specifically what the second equation on this page says. I would get M1G, there's the force, the weight due to M1, times x1. Now, these two forces are this force and this lever arm that I'm calling it. They happen to point in perpendicular directions. That's why this is the extent of the formula. Once we learn torque, there's going to be a sign that has to go in there, SINE, the sine function that relates to the angle between the quote unquote lever arm, which would be a vector that points from the fulcrum or the axis of rotation to the point of application of the force. That is a vector quantity, and its magnitude would be x1 or x2. And now, if that vector is perpendicular to m1g, which is the weight, and therefore is vertical, then the sine of 90 degrees is 1, so you get just m1g times x1, just like we have. So that's what's going on here, and later, like I said, when we learn about torque, it'll make a little bit more sense. But what we see here is now we have m1g times x1 plus m2g, there's the force again, times x2. Those two are going to tend to rotate the plank in a clockwise rotation. The right-hand side is going to go down and to the left. Now, to counteract that, we'd like to find one place where we could put that total mass, m1 plus m2, on the left-hand side. That distance I'm going to call XCM. And it should behave just like the center of mass because we're basically finding something that exactly cancels out the motion of the right-hand side uh, by doing exactly the opposite, but with the exact same forces. So in some sense, the mass big M, which equals in this particular example M1 plus M2, is acting just like a point particle with exactly the same net force acting on it as was acting on the system M1 plus M2. So the system, though M1 and M2 aren't necessarily connected, they can still be M1 plus M2 even if they're not connected. So doing that, we see that we get M times G times XCM on the left-hand side, and M1G times X1 plus M2G times X2 on the right-hand side, keeping in mind that M, the thing we put on the left, has to be the sum of the two because we want it to have the same mass in order for it to be a candidate for the center of mass. Now, if we continue to do this for n particles, we'd get m1g times x1 plus m2g times x2 plus dot 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 on up to m sub n g times x sub n. Again, we want to define the center of mass XCM such that XCM times that total mass M1 plus M2 plus dot 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 on up to plus MN. If that particular point particle was placed at that distance XCM on the left, then it would completely balance. So that turns out to be really what the solution is. So in general, we can actually set the two equal to each other. We see that all the terms have a common factor of g. So after dividing both sides by the common factor of g, we end up getting m, which is m1 plus m2 plus m3 plus dot 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 mn times x center of mass is equal to m1 x1 plus m2 x2 plus dot 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 mn xn. Generalizing, we can increase this to include not only the x, but also the y direction and the z direction, and we can solve for xcm. And this time we're going to actually use the fact that m is equal to m1 plus m2 plus mn. So we divide both sides by big M, which is M1 plus M2 plus M3, so on and so forth. And we get XCM is equal to M1X1 plus M2X2 plus dot 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 on up to MNXN, all divided by the total mass M1 plus M2 plus M3 plus dot 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 Mn. Similarly, Y center of mass will be defined the same way, and Z center of mass will be the same way. So that gives us a general formula for calculating the center of mass of an object made of a certain number of discrete point particles. It turns out that if you are dealing with, instead of discrete point particles, you're actually dealing with discrete particles that have a physical dimension, then you can use the definition of center of mass to help you there too. So you can still put M1 and put its center of mass at a distance x1, and that counts just the same as if it was a m1 point particle at a distance x1. And again, you do m2, you find the center of mass for the object whose mass is m2, and you put that center of mass right at a distance x2, and you get the same formulas. So it does generalize that way where you don't have to actually just be point particles. And you'll see later I have a problem where I'm working with a framing square to calculate the actual center of mass of the framing square. So you'll see an example of that, in which case you're using not point particles, but you're using physically sizable, non-microscopic discrete particles or discrete objects. And again, discrete just means countable. Whereas like even grains of sand are technically countable, but if you try to count bits of mayonnaise, for instance, that's more like a continuous object. Now, if you got small enough with a microscope or something like that, then yeah, mayonnaise would break down into individual molecules. It's a mixture really, but it's a mixture of molecules and atoms. And once you got small enough to see the individual atoms and molecules, then it would no longer be a continuous chunk of matter. It would be discrete. But if you stay quite a bit above that, where atoms and molecules are coming into play, mayonnaise just looks like a continuous chunk of matter. Not necessarily a hard one unless you freeze it, but still. All right, so now that we have that, we might also want to address how do we go about calculating the center of mass if the object's not made up of discrete countable number of objects? Well, if that's the case, you might want to divide the actual object, which could be, for instance, this water bottle again. You could say, okay, well, this looks like a continuous chunk of matter. Maybe we'd take a itty bitty piece of it and then say, well, how do I deal with that? Well, with that itty bitty piece, what we're going to do is say, well, I got to have some way of accounting for the mass of that itty bitty piece based on its physical dimensions. So in order to do that, we have to bring up something called density. And specifically, we're going to talk about a linear density, a area or two-dimensional density, and a volume density. And what it is just a way of us taking a certain physical dimensional size of a chunk of matter, and from that physical dimension of a chunk of matter, getting out the actual mass of that chunk of matter. So we could imagine, for instance, a little piece of something infinitely thin, like a long piece of string, or let's say this wire here. Notice the physical dimension up and down is very thin. The physical dimension in and out is very thin, but this dimension this way, left and right, is quite long. So you can sort of pretend like the vertical dimension and the in-out dimension are essentially zero, so that it has no physical size. And then the only size that matters is how long it is from here to here. So if you shrunk that up into an itty bitty piece, because there's some chance that, one itty bitty piece of the wire might be really light, whereas this piece of the wire might be made of lead and be very heavy, and this piece of the wire might be somewhere between, right? So if you divide it up in small pieces, then you might say, okay, this little length right here, I'm going to call delta L. That's a lowercase delta. So you see the symbol right here. So that's the delta L. And what you'd like is some number that you can multiply by delta L to get delta M. So the mass of this little chunk would be delta M, its length would be delta L, and the number lambda, which we call the linear density or the line density or the mass per unit length, that would be a one-dimensional density function. And it could be a function or it could be a constant. In fact, when we talk about something being having its mass uniformly distributed, what we mean by that is that the constant, or the lambda in this case, would actually be a constant. If it's not a constant, then it's not uniformly distributed. Now, again, we might not also have something that's one-dimensional. We might have, for instance, a sheet of paper, which is obviously very, very thin. So this dimension is almost nothing, but this dimension, macroscopic. So it'd be nice if we had some kind of form or some kind of way of taking the physical dimensions of the width and the height and making out a mass. Well, in that case, what we're going to do is we're going to say that there's a quantity called sigma, which is the area density. And if we call the area sigma A, that could be length times width, for instance, then sigma A would be the area. If we multiply that by the, or excuse me, delta A would be the area. If we multiply that by sigma, then we'd actually get the mass. So delta M, the mass of the rectangle, would be sigma times delta A. And similarly, if we went 3 dimensions for a chunk of matter, for instance, like just imagine this being a cylinder, a uniform cylinder, then we could say delta M is equal to some density. In this case, we call it rho times delta V. Now, in all of those cases, we are dealing with with small, but not necessarily microscopic stuff. If we wanted to consider, because for instance, individual slice of matter might be slightly different in mass than a identical slice from somewhere else. So you'd want to divvy it up so small that at least each individual piece is constant throughout. If you did that, you could imagine taking the limit as the delta L, for instance. That's a small length is now going to become infinitesimally small. So you take the limit as delta L goes to zero. That delta L then becomes a dl, like we know from calculus. Similarly, a delta A becomes a dA as we allow it to get infinitesimally small, and a delta V, a small volume, becomes infinitely small as we take the limit as delta V approaches zero. And then instead of delta M equals lambda dL, we get dm equals lambda dl. And just for the record, that means lambda would be dm over dl. That's another way of solving for it. And specifically, the units of lambda would be kilograms per meter or kilograms per centimeter or something like that. Similarly, if we took a two-dimensional thing, what we call a lamina in mathematics, like a sheet of paper, then if we took the limit as the delta got really, really small, it would become a differential, and then it'd be dm is equal to lambda dA. Again, the sigma, excuse me, I said lambda. The dm will become sigma times dA. And in this case, the sigma would have units of kilograms per meter squared. And again, if we took a three-dimensional object, the delta M and the delta V would, in the limit as delta M and delta V approached zero, they would become differential. So we get that dm is equal to rho times dV, and the units of rho would be kilograms per cubic meter. So all of those are different types of densities. And again, if the object had its mass uniformly distributed, that would mean lambda or sigma or rho would be a constant. So now that we've gotten a way of getting the mass out for a itty bitty chunk of material, because you really want the chunk to be small because you need to make sure they all have the same x distance from the y-axis and the z-axis, for instance, the distance x is how far that thing acts like a point particle is away from the quote-unquote potential rotation axis. So divvying that up that way, the natural extension from these equations, m1 x1 plus m2 x2 plus m3 x3 plus dot dot dot, all over m1 plus m2 plus m3 plus dot dot dot, the natural generalization of that is xcm equals the integral of xdm divided by the integral of just dm. Similarly, the ycm equals the integral of ydm divided by the integral of dm, and z center of mass equals the integral of zdm divided by the integral of dm. In all these cases, the dm we're going to assume is either lambda times dl. Again, lambda could be a constant or it could be a function. The dm could equal sigma dA. That's when it has some kind of two-dimensional symmetry usually. Or dm could be rho times dV, and that's where it has a three-dimensional shape. Reading and studying a few examples and then calculating the centers of mass for discrete and continuous bodies is really the best way to learn it, and then just try your own problems and work as many as possible. So hopefully this will help you better understand what center of mass is and how it's calculated. From here on out, I'll just be doing examples. So I hope that helped. Have a good day. Bye.